So this is an important session for the Society. As many of you know, the Society takes great pride in awarding PhD theses and outstanding young colleagues. This is done through a nomination process where people submit their nominations and the President appoints a committee that evaluates each nomination. And once they make a decision, they are announced. Before 3 years, we used to offer the PhD awards only once every 3 years, but since the field is growing, we have now decided to offer it every year. So that is the reason why you see 3 PhD awardees here. And this year we also had an unusual but a good situation that the committee decided that we'll have a joint winners for also the Young Scientist Award, essentially. That is for a young scientist with outstanding publications. At this point, I should also thank Paolo, Alexandra, and the organizing committee for waiving the registration fees for the award winners. And the Society supports them through a prize award and also some a travel grant. So it is, I'd like to make 2 points. Colleagues that you have, students and young researchers, please nominate them. Only if they get nominated, they get considered, so please nominate them. It's a fantastic opportunity. And the next one is for all the awardees. With great awards comes great responsibility. So we look forward for your continuous support to the Society and to pay it forward to other young people. So please engage yourself with young people. They really look up to all of you as future leaders in this Society. So without any further delay, let me first introduce Nick Wilkins, who received his PhD from the University of Alberta, and now he's with Svante. Nick, please.
Thank you, everyone, for coming to my talk today. As I've mentioned, we give these now pretty frequently, once a year. This was actually done immediately after the last FOA, about 2 weeks after I defended my thesis. So it's all of this, for the most part, is published, and I'll be giving an abridged version of it today. Okay, and this is an awards talk. I'd like to take a moment and thank the people and organizations that made this possible, including Arvind as my PhD supervisor, as well as my co-supervisor, Stephen Kuznicki. Without them, this would not have been possible. I'd also like to thank a formative mentor of mine in experimental techniques, Jim Sawada, and a frequent co-author of mine. Here are all the organizations that made the work possible, and of course, the organizations that got me here today. All right. Computational pressure and temperature swing adsorption, process design, and optimization requires reliable multi-component adsorption equilibrium data to accurately assess process performance. There are some cases where if you do not have this data, you can predict it. And this is actually something I had to do in the last chapter of my thesis with a methane nitrogen system that we thought was interesting. And we did some process simulations using extended isotherm models. I don't have enough time, unfortunately, to talk about this today. But the caveat is that these are often inaccurate for non-ideal systems. And in these cases, we highly suggest that you measure the data yourself. The good thing is there are many techniques in the literature to do this. The bad thing is many of the people who know that have done these, they're quite difficult and often require custom-built instrumentation. One of the more common ways to do this is using dynamic column breakthrough, or colloquially we call them breakthrough experiments, or abbreviated as DCB. A DCB experiment essentially is a packed column. We measure its effluent change in composition and flow to a change at the inlet of the column in composition and flow. When it comes to an equilibrium, we can solve a transient mass balance and get an adsorption equilibrium loading for every component that's absorbing in the system. These are quite useful for multi-component measurements in particular because we can actually pick the temperature, pressure, and gas composition before an equilibrium, allowing the easy construction of phase diagrams. And of course, this is a nice visualization of the data and allows us also to check against multi-component isotherm models that you would put in your process simulations. But as many people who have run these know, they can be quite difficult sometimes to interpret, and in some configurations and styles of running these experiments, there can be quite a lot of error in the measurement. So that brings me to the 2 topics I will talk about today in this thesis, which is major themes that were throughout the thesis, but minimization of error associated with DCB measurements, and proposing new protocols to measure equilibrium in challenging systems. Before I get to any of these studies, though, I need to give you a bit of background of DCB. I have a schematic here And the heart of the system is just an adsorbent-packed column with the adsorbent of interest. Upstream, we have this valve, and we have one of two gases that can flow through. The top one I'll just consider the initialization or sweep gas. It's something that we use to prepare and regenerate the bed. And this one down here, we'll consider the test gas. These are the adsorbates that you wish to actually measure some equilibrium or diffusion data in the bed. And then downstream, we have a composition and flow detector, which are required to close the transient mass balance. There are two common ways that you can run these, or many others in the literature, but the two I'll be talking about today are what we just colloquially call the adsorption and desorption experiment. And this one here is an adsorption experiment in composition and flow. The way that you would run these with a previous setup is you first initialize your bed with the sweep gas when it's at an equilibrium. You flip from that upstream valve to the test gas, and you measure the effluent composition, the red one, and the flow curve. And when these reach an equilibrium, where you see the outlet conditions at the inlet conditions at the outlet of the bed, we can then close the transient mass balance. There's one important consideration that sometimes is skipped in the literature, and this is we have to also include the fluid accumulation in our bed, sometimes called a blank measurement or a dead curve. And this is very important depending on how you actually construct your instrument, and for milligram size samples, it becomes extremely important, especially with weakly adsorbing materials. After an adsorption experiment's done, you can immediately run a desorption experiment. And this is done just by flipping that upstream valve back to the sweep gas, measuring the effluent composition and flow curves again. And as I mentioned, you can solve the transient mass balance for this one as well. The math changes very slightly. And if the experiments are run very well, you'll find that the two methods agree with each other exactly. It's a great way to check experimental consistency. There is one complication with the desorption experiment, and it's a bit harder to get this data correct. And it's that you have this changing composition and flow curve at the same time, which can be a large source of error depending on how difficult it is to calibrate your effluent mass flow meter. Okay. All right. The way that I often show these, and quite a few people now in the literature are showing these, is as a combined term, so including the effluent composition and flow. And the reason why we like to do this is then the breakthrough curves will actually show you your molar accumulation, where the mole fraction curve itself doesn't actually show the entire picture. Here I have the adsorption and desorption experiment, and as you can see, this red highlighted region is actually proportional to the adsorbate loading in the system. I've shown this as Q star in these, and part of the reason why we also like this normalized molar flow that we call it is it shows up in the mass balances themselves for either the adsorbing or desorbing experiment. Okay, without further ado, I'll talk about the first study that I'm going to highlight in this thesis, and it's the accurate measurement of the light component loading in a highly selective multi-component system. Okay. This actually, at first, didn't start off as a metrological experiment. We were just interested in looking at VSA loadings for, at the time, a very common carbon capture system, which was Zeolite 13X. Obviously, now it's not really considered as a viable carbon capture adsorbent, but at the time it was considered just because it has a very high selectivity of CO2 compared to something like nitrogen. And because of that, we found the first problem with our experiments. When we tried to measure loadings for VSA relevant conditions, so less than 1 bar total pressure, we run adsorption experiments for CO2 and nitrogen. In this case, we used helium as our sweep in regenerating gas. We found that carbon dioxide, we can close this mass balance very easily, repeatably, with low error. Nitrogen, the curves look very similar every time you do this, but you get wildly different calculations, sometimes even negative calculations, and we were very intrigued by this result. It gave us a bit of a headache, but also a fun problem to solve. I'll show you a hypothetical example that finally got us to understand what was going on. Same type of system, just hypothetical adsorbents. We have the adsorption experiment, and we have the desorption experiment here, run in the same way, where we have an inert sweep first, binary heavy light system, and then we sweep that heavy light system out with an inert sweep. The light component shown in blue, and the heavy component is shown in red. So in the previous system, nitrogen would be our light component, CO2 would be our heavy component. If we look at the molar accumulation, they're actually shown by these areas up here for the different types of experiments. And the one that obviously we were having an easier time measuring was the carbon dioxide, this area C. And one of the things that's very key is that the signal is actually 0 until you actually hit a breakthrough. And because of this, there's no accumulation of error until you see the breakthrough itself, of course. The light component, however, breaks through very early, and then it does not come to an equilibrium. It's slowly being pushed out by the heavy component, and then we see this roll-up phenomena, and finally, when we come back to the feed concentration, we have reached an equilibrium. But this is a relatively very long time to accumulate error, and this is why we found negative loadings. You're subtracting this area A, the overloaded portion, from B, the desorbed portion, and B has a massive amount of error associated with it. So we often found area B experimentally was just larger than area A. And this, unfortunately, is just a fundamental part of this type of experiment for a highly selective system. There's a very easy way to get around this, and since this work has been done, there's many others in the literature too, and they all work quite well, depending on what system you're looking for. But the way we did it was we decided, okay, we're just going to focus on the heavy component in the adsorption experiment, and then we run a desorption experiment immediately after to get the light component loading. This has no subtraction, so it's guaranteed to be positive, and the experiment time is much shorter, so there's not as much accumulation of error. So we did this with the same system that we were interested in, CO2 and nitrogen on 13X. This is at 22 degrees Celsius for a 1 bar and half bar total pressure. CO2, of course, we got with the adsorption experiment since it's the heavy component. Nitrogen, we got with a desorption experiment following the adsorption experiment. And as you can see now, these loadings are positive and the error bars do not bisect to 0. So it's a reliable measurement here. We wanted to make sure too that this was generalizable and it didn't just end up working for our system. We were also interested in water on Zeolite 13X, but I can't talk much about the conclusions today. So we did this replacing nitrogen with water and using helium as an inert sweep. We ran, in this case, water is going to be the heavy component and CO2 will be the light component. And when you run an adsorption experiment in the same way, we measure the water loading using our adsorption experiment, and these data is shown up here on the phase diagram. CO2 is measured using a desorption experiment following the adsorption experiment, and these are shown down here. These are actually shown, as circles down here. The triangles are actually an independent measurement, which was our first confirmation with a separate measurement that this technique is valid. So we use thermogravimetric analysis, and Zeolite 13X with CO2 water is one of the few systems where you can make the assumption that CO2 isn't displacing water in that system. But as you can see, they're all non-zero. They're also quite low in loading. About 99% of the capacity is killed compared to a 1 bar CO2 mixture. And of course, the error is good in this system. Okay. For the second part of this talk, I would like to talk about measurement of unary and binary equilibrium on very small sample sizes using dynamic column breakthrough. Okay, so in the previous talk, the previous section of the talk, I was using a column that was fairly large. It had about 20 cc's of volume, about 25 or so grams of Zeolite 13X. Obviously, when you're creating novel materials, this is a very large value. But when, oh, that was too forward. For many quantitative experiments, though, that we do, dynamic column breakthrough is often considered as like 10 to hundreds of grams of material. Novel syntheses of materials, though, will be a couple orders of magnitude smaller than that, usually on the order of tens to hundreds of milligrams instead. And of course, it's a huge effort to scale these materials up to put into a traditional breakthrough apparatus. So the idea we came up with is there a way that we can measure this at these small scales so we can more efficiently pick materials for separations of interest, find their binary equilibrium, and then be able to start doing process simulations with these? The good thing is the answer is yes. You can use dynamic column breakthrough measurements at these scales. It was actually known before the work that we do here. We just spent a lot of time trying to show how you can do these and do these accurately with this. And essentially, it requires a dedicated instrument and understanding the challenges of miniaturizing these experiments. So I have a picture of the apparatus here, and I see some of Arvind's students here who are frequently using this instrument now, which makes me very happy. And we have a schematic here. This is both shown in the paper that we published at the end of my thesis. We call this the microscale dynamic column breakthrough apparatus, or micro-DCB for short. And it's built entirely into a turnkey gas chromatograph. There's many reasons why we did this. The first one is that we get to use the oven as a thermostat, It has a highly accurate thermal conductivity detector, which gives us a very high accuracy effluent composition signal. It allows us to also tie everything to a common clock to make data processing slightly easier. All the other instrumentation is fairly standard, but there's an emphasis on miniaturization and high accuracy measurement. There is one aspect I need to talk a bit more about, and it's this long length of tubing you see here. After the TCD and before the mass flow meter, you can actually see it as this copper coil down here, and we've used different variations of this depending on how strong the adsorbate is. But its purpose is to split the composition and flow fronts from each other. As I mentioned, the effluent flow calibration can be a high error part of your measurements, but if it's in a single composition fluid, the calibration becomes much more accurate and easier. Essentially, if you put this at a far residence time after your composition measurement, you decouple them, you measure your flow event, since it's a pressure wave, in a single composition fluid. It's a one-point calibration. You can do it before every experiment, and it makes it essentially ties the error to your upstream measurement, which in our case we use a Coriolis, which is very accurate. So it eliminates a massive source of error in your instruments and your measurements, and one of the huge benefits of miniaturizing these systems. Technically possible at large-scale systems, but it might be impractical. Okay, so the aim here was to see, can we do this accurately, and develop techniques to do so. So this was using Zeolite 13X again, the same sample as before, but as you can see now, it's a couple orders of magnitude smaller, about 240 milligrams. And we started with unary systems, mixtures in helium, to see how well an instrument like this would work. We did this for nitrogen, methane, and carbon dioxide. A single experiment at 30 degrees for carbon dioxide. And then for nitrogen and methane, these were experiments at 30, 40, and 50 degrees Celsius as 25, 50, and 100 mole % mixtures, both adsorption and desorption experiments. As you can see, they agree with the volumetric data, which is shown in circles, squares, and triangles very well. It's usually within 1 to 2%, but could be as maximum of 5%. The next one that we tried was a binary measurement. And in this case, obviously, they get much more complicated. There's a lot more things to worry about. So we picked an easy binary at first. This is methane and nitrogen on Zeolite 13X, and we did this at 30 degrees Celsius in about 1 bar. The reason why we picked this is they both exhibit linear isotherms at these conditions. So they should follow ideal adsorbed solution theory. And ideal adsorbed solution theory predicts that they will adsorb as their unary components. So we can draw our methane unary isotherm and our nitrogen unary isotherm here. In this case, we did true binary experiments. So this is just, the TCD is blinded to one gas and measures the other. In this case, it's a 50-50 mixture of methane and nitrogen for adsorption, desorption. We close the mass balance and find it's directly predicted. Oh, that's the wrong direction. We did the same for nitrogen now in this mixture, and again, we find exactly what we expect. We did this for other measurements, as you've seen. There's many more in the thesis and paper as proofs. But the real thing I would like to highlight with this is not only its accuracy, but an elution profile, a combined adsorption-desorption experiment, only took about 35 minutes. So including all blanks and experiments done, this phase diagram only took 10 hours to make, which is a long day in the lab. For those of you who have made these before, at a large scale, these usually take multiple weeks. In my water case, it took a couple of months. So it's a huge scale up in terms of time. But this is also an ideal system. We wanted to see, do these conclusions hold in a non-ideal system? And at the time, we had read a paper by Krishna and Van Batten that used molecular simulations and found that there was non-ideal effects of mixtures of CO2 and methane on Zeolite 13X. So we decided to take that as a test case. We considered this is at 30 degrees Celsius for mixtures of 5% CO2 to 75% CO2 in methane. And we found exactly the same conclusions with our instrument, that carbon dioxide is essentially unaffected from methane co-adsorption, and methane is actually a positive deviation from ideal adsorbed solution theory. It absorbs more than the theory predicts. This did take slightly more time, as expected. We had to regenerate the sieve between carbon dioxide measuring experiments, but still, it only takes 24 real hours to do this, so 3 days in the lab, opposed to, again, a couple of weeks for an equivalent system. All right, so I've talked to you guys a lot about multi-component equilibrium using dynamic column breakthrough today. I highlighted 2 key results from my thesis, which is the measurement of the light component in a highly selective system using CO2, water, and nitrogen, in that. And essentially, our protocol prescription was to say, measure the heavy component in the adsorption experiment, and then run a desorption for the light experiment. We also highlighted the benefits of milligram scale quantification, and in specific, it seems to be extremely fast and actually can eliminate some sources of error. All right. Thank you for coming to the talk. I hope I didn't run over too long.
Nope. Thank you. Thank you, Nick.
Yeah.
The floor is open for questions.